By the way, please feel free to ask any questions during the talk, but we can also discuss after the talk as well. So it's on you. Thank you.
Thank you, Aydin, for the kind introduction. And of course, thank you to the organizers for inviting me to this great seminar series and giving me the opportunity to kind of talk about some of my work today. So this is kind of a project that started while I was at MPI with Roederich and Schuberl, kind of thinking about chaos in classical many-body spin systems. Given by the kind of recent interest that came from quantum mechanics, where kind of the OTOC was kind of rediscovered and people were very excited about it, and we kind of were wondering, can we kind of say something smart about OTOCs in classical systems, given that we believe we understood classical spin system decently well. So these are kind of the first two projects. So one is kind of now, I guess, 4 years ago, which was the chaotic spin liquid work. The second one was, excuse me? I have some kind of feedback. Okay.
Yeah, I think someone was unmuted.
Okay. Right. The second work was kind of published last year, which was kind of asking the same questions across a thermal phase transition. And then if we have time at the very end, I could also briefly go through a very recent project this week accepted in PRBR, where we kind of look at anomalous hydrodynamics in spin chains. And with that, I guess, let me get started in the kind of the overview. So kind of the basic questions I'm going to ask is kind of how chaos in many-body spin systems behaves. So specifically, I want to ask, how does it kind of show what is phenomenology, as well as how can we describe and characterize chaos in these systems, as well as asking, can we connect these kind of very quantitative notions that we get from microscopic spin simulations to more macroscopic notions in terms of transport. And then in the second part, do these kind of phenomena we find in the chaotic spin liquid change once I also allow symmetry breaking, or equivalently, when I allow classical order and quasi-particles, which in this case will be spin waves, emerge in our system and could modify what we find in kind of the spin liquid case. And specifically, what we are going to use to kind of quantify chaos is kind of the butterfly effect, or more specifically, both the Lyapunov exponent and the butterfly velocity, which kind of characterizes the temporal growth and the spatial spread of a perturbation. And you could, of course, ask, why are we the ones asking these questions? And why are we asking these questions now? Kind of classical chaos has been known for a very, very long time and has been studied in a multitude of settings. There's kind of two reasons why we got interested in it. Kind of one was, as I mentioned, these emergence of OTOCs in quantum systems, which kind of allows you some notion of quantum chaos. And we were wondering, does this actually make sense in a classical setting where we understand chaos reasonably well? So can we transfer these OTOCs and then learn something new about classical many-body systems, as well as learn something new about OTOCs using a classical system? And then secondly, there have kind of been new spin liquids, classical spin liquids that have been discovered that actually make this a lot easier or simpler from a numerical perspective. So these new spin liquids actually allow us to ask these questions in a very reasonable, simple fashion. And then why would you ask these questions in classical systems? Of course, quantum chaos is kind of cool and interesting. So why do it in a classical setting? So one big advantage we have is that we can access length and time scales in interacting systems that are way beyond anything you could dream of doing in quantum systems typically. So we can easily do 1 million spins, and we can easily go to 10 to 6 times the exchange constant to really ask questions where chaos connects to macroscopics, which typically would be extremely hard to do in an interacting quantum system. And then the kind of specific platforms we're going to use is kind of a classical, which we call a Z2 spin liquid. And they have the most important property in this talk of classical spin liquids is that they don't order down to 0 temperature in this case, and they don't have quasi-particles. And in the second part of the talk, I will contrast that situation with the one of classical ferro and antiferromagnets, where you kind of just get classical order and well-established spin waves in the low temperature regime. So with that, I want to briefly talk about chaos. Chaos is great. And I've already talked about the butterfly effect. And I kind of believe it's intrinsically fascinating as kind of a property that only emerges in many body interacting systems. So it's really something that requires interactions. It's not something that happens in a single particle system. It is also important in terms of fundamental physics as underpinning thermodynamics. And generically, kind of many body systems are chaotic. And for this talk, let's say also ergodic. There's, of course, a few notable exceptions that are important recently, namely integrable systems or many body localized systems, as well as systems that have constraint dynamics, fracton phases, or systems that show many body scars. And I think you had a few talks on those topics in the seminar series already. So I'm not going to talk about it at all. So all my systems will kind of be fully chaotic and ergodic. And finally, you could kind of ask about basic connections between classical and quantum systems, something that I've already alluded to. So these OTOCs came from the quantum realm. We are kind of wondering in a spin system, which in some sense you could imagine is quantum, because spins do not exist classically. Do these notions make sense? As well as asking, given that this is a spin system which has a well-defined classical limit in the large S limit, do we actually learn something new about these notions that came from quantum mechanics? So with that, let me kind of introduce the kind of main player that we're going to use to talk about chaos here, which is kind of the butterfly effect. And the important thing to note is that it is a spatio-temporal phenomenon. So what people have known for a long time and used is in many body systems, typically you observe a sensitive dependence on initial conditions, which means that an initial perturbation can grow exponentially fast in time, which then defines a Lyapunov exponent just as the coefficient of this exponential growth. And in the story, that's just a statement that the butterfly wing beat, a small event, can lead to a huge event like a tornado. So this is something that people have been studied for a long time in kind of classical systems in terms of chaos. Kind of a new thing that kind of the OTOC kind of allows is that it also has a spatial component. So this perturbation can propagate in space, which again in the butterfly analogy means that the weather event actually takes place far away from the butterfly wing beat itself. And that then often happens ballistically. And if it does happen ballistically, you can define a speed of a wavefront of this perturbation. And kind of the image I'm showing here is actually a spin system simulation of about 40,000 spins, where we kind of see this propagating wavefront, which actually propagates ballistically. So in some sense, what is new in using this OTOC notion is actually that you can talk about spatially resolved chaos. We, for a long time, have looked at Lyapunov exponents and kind of considered how they depend on systems and parameters. Often people in the classical chaos literature haven't looked at how it behaves spatially. And that's kind of now what this OTOC allows us to do. So the OTOC itself, you will be very familiar with that by now, is just kind of a squared commutator and the expectation value of that. So typically you have two different operators, and one operator will be at a later time and at a different spatial location, whereas one, say, would be an initial position at an initial time. And intuitively, you're kind of asking, what does a perturbation induced by operator V do at a later time at a different perturbation to the expectation value of an operator W? And this was actually written down first in 1969. It has been rediscovered, I guess, now 15 years ago in quantum mechanics, for the reason that this quantity actually shows the butterfly effect also for quantum systems. So it shows exponential growth and ballistic spreading of a perturbation. And there's also kind of this quantum chaos bound, which kind of was shown in 2015, where this Lyapunov exponent extracted from an out-of-time order correlator is actually bounded by temperature for the maximally scrambling systems. So this has been studied in many, many systems. So it has both been experimentally studied in a variety of systems and has been theoretically studied in random circuits, in random Heisenberg chain, in Lagrangian liquids, in a periodically driven system, in black hole systems, and in large N theories, or in SYK and holographic systems. And the phenomenology is always that there's a propagating wavefront, it spreads ballistically, and some form of exponential growth at the very wavefront. So this now came from quantum mechanics, and now we wanted to ask these kind of questions in a classical setting. And that was done in 2018. So for a classical spin system, you can write down an analog of the quantum OTOC in terms of Poisson brackets. So you kind of can recognize this, what we call a decorrelator, is essentially just replacing the Heisenberg, commutators with Poisson brackets, and then again having two operators, one spin operator at the lattice position x at time t, and one operator acting on the zero spin at time 0, and then you square it and you take a thermal expectation value of that. You can then show that to linear order in perturbation theory, this Poisson bracket squared is the same as asking what is the deviation of a perturbed trajectory squared. And that is then what we define as the decorrelator. And this kind of connects the classical notion where you're asking, what is my sensitivity on initial condition? So how does my trajectory diverge with time after a perturbation directly with an object that looks like the classical limit of an OTOC? So that is exactly this intuitive notion. This delta S is just defined as the difference of a perturbed initial state and the initial state unperturbed versus time squared or spatially resolved. And it is a semi-classical version of the OTOC. And this is the other thing I mentioned. So in some sense, these Poisson brackets also allow you natural semi-classical limit, where you just send the spin length of a quantum system to infinity and kind of recover classical dynamics. So this was done in 2018. Since then, it has been used again in a variety of settings. So there was the original work in 2018. There's our work, the first work that I'm going to discuss, which is kind of using this to study the temperature dependence of chaos in a kind of chaotic spin liquid. It has also been applied in kind of fluids. It has been applied to studying phase transitions, I think specifically the phi to the 4 model, kind of a classical field theory model. It has also been kind of looked at in kind of XXZ models, as well as in cellular automata. And the last work that I'm going to discuss, which is the work where we kind of look at it in classical phase transitions in Heisenberg models. So that's to show this kind of classical notion has actually led to a variety of works that kind of use this to explore classical many-body chaos. So with that, kind of let me kind of go to what we are going to do. So we are asking some specific questions, mainly, does this notion of chaos actually persist from the ground state up to the infinite temperature state where classically chaos is very well established? If it does, how does chaos behave as I go to the low temperature regime? And what do these classical OTOCs actually tell us, if they tell us anything? Then those kind of specific questions kind of relate to the fundamental questions I already mentioned. So relations between these microscopic chaos notions and macroscopic kind of transport dynamics, as well as the effects of thermal phase transitions, symmetry breaking, and quasi-particles. And the kind of platforms we're going to use is this classical spin liquid, which kind of has dynamics down to 0 temperature and no ordering transition at all, to be contrasted with a classical ferromagnet where you have a thermal phase transition and quasi-particles. And with that, let me kind of briefly give an introduction to kind of spin liquids. So from a high-level perspective, typically, if you have a kind of an ordered system or a system with wood order, you kind of find the variety of classical ferromagnets or antiferromagnets. You can then induce something that we call geometric frustration, where the interactions cannot all be satisfied at the same time, or alternatively, where you have competing interactions, which then destabilizes conventional order and allows you to get this spin liquid that is non-ordered down to 0 temperature. There's, of course, also another way to destabilize order, which is just thermal fluctuations. Whereas at 0 temperature, a classical spin system on a bipartite lattice will be perfectly ordered, either in a Néel state or say in a normal ferromagnet. If I add thermal fluctuations, that can kind of melt this order, getting you kind of a paramagnetic unordered regime. In contrast, in a spin liquid, where you kind of have this geometric frustration, say as on a triangle, you can't satisfy all interactions at the same time, which then also suppresses order. In contrast to thermal fluctuations, this, however, gives you a regime where the system is still strongly interacting, but still not ordered. And that's kind of this spin liquid or cooperative paramagnet. With that, kind of let me go to the models we're actually going to discuss. So what I'm going to talk about are classical Heisenberg magnets. So it will be O3 spins on lattice sides with an exchange constant J. And the coupling will typically be nearest neighbor or close to nearest neighbor between those. And I'm going to look at ferromagnets, which would be negative J, and at antiferromagnets, positive J. And then for the classically ordering system, we are going to look at those at kind of 1D spin chains on 2D square lattices or on 3-dimensional cubic lattices. In contrast, the kind of spin liquids are defined on these kind of frustrated lattices. So specifically, I'm going to consider a Kagome lattice where the spins kind of sit on corner-sharing triangles. And then there's a few types of spin liquids. So the well-known ones was the U1 Coulomb spin liquid, which has been known for a long time. The more recent one is the 2 spin liquid that I'm going to discuss in a bit more detail next. And then there's also disordered frustrated spin liquids. And the main property of them is essentially they don't have order. So specifically, if you look at the structure factor, you don't see Bragg peaks, which you would expect for a ferromagnet or antiferromagnet that actually establishes long-range order. That brings me kind of to my first part of my talk, which is kind of the chaos in a classical spin liquid. And I want to briefly introduce kind of what this Z2 spin liquid actually looks like. Again, those are Heisenberg O3 spins on the Kagome lattice. And it's not quite nearest neighbors. In this case, all spins in these hexagonal plaquettes will interact. So the Hamiltonian is just summing over all pairs in these hexagons. And you can actually exactly rewrite that Hamiltonian as a sum over the total hexagon spin squared. So L alpha is just summing all spins in a given hexagon alpha, then squaring this total hexagon spin. And that already tells you another property of these classical spin liquids. You can understand ground states, since this is a positive Hamiltonian. A ground state, if it can be satisfied, is a state that has L alpha equals 0 on all hexagons. So this essentially gives you a constraint set that defines the ground state manifold. And if you actually count how many constraints you have versus how many spin degrees of freedoms you have, you will realize that this model is actually under constrained. So in principle, there's many states that satisfy this condition. And this is the second property of classical spin liquids. They have an extensive ground state manifold of exactly degenerate states. And that is the other reason why you can avoid order, because you have extensively many states to choose from. So this, I already told you, there's no order even as you go to 0 temperature. Moreover, this spin liquid actually has short-range correlations, which means they are actually exponentially decaying in the distance at any finite temperature, rather than power law correlations that a kind of U1 spin liquid would have. And what we are going to do is we kind of just going to look at the semi-classical dynamics of this spin system, which is kind of induced by the Poisson bracket. And that is just precessional dynamics of each spin in the exchange field induced by its hexagon neighbors. And then we're going to sample a thermal ensemble just from the via Monte Carlo from the Boltzmann distribution for this Hamiltonian. So one thing that is worth mentioning is that the dynamics itself conserves energy and total magnetization, whereas the ensemble is, of course, defined with a fixed temperature beta. So that is to say, in principle, any quantity I extract from these dynamical equations is independently a function of energy and magnetization, whereas the ensemble I use defines a joint distribution of energy and magnetization that will depend on the temperature and on system size and other properties. So with that, let me briefly talk about the thermodynamics. So one quantity you could consider is the spin autocorrelation function, which is essentially asking, does a spin remember its past? So this is on the same lattice side, but at a time distance. So it's really just asking, do I move away from my initial state? And in this Z2 spin liquid, the dynamics will always be relaxational, by which I mean it will actually decay exponentially in time with a coefficient kappa, which you can extract as a function of system size and temperature. And what you're going to see is that this kappa is actually linear in temperature, but it is always finite for any given temperature. So the system is always fully relaxational which wouldn't happen if you have order, because then this would pick up a finite magnetization value rather than decaying down to 0 exponentially. In addition, you can consider the spin structure factor, which is the space and time Fourier transform of the spin-spin correlation function, now at different time points and different lattice sides. And this in the Z2 spin liquid will be fully diffusive. So specifically, you can consider the spin structure factor close to Q equals 0, and you will see that this actually scales with the normal kind of diffusive form. In addition, as I already told you, it doesn't have any Bragg peaks. So this structure factor as a function of temperature always kind of has a broad continuum and no peaks at all. So this is kind of a classically picture of the spin liquid. And this gives you the thermodynamics of the states we are essentially sampling via Monte Carlo. With that, I now want to go to kind of the actual decorrelator, which I've already introduced before. The simple protocol we're going to use is we sample an initial state via Monte Carlo, and then we perturb this initial state via a rotation, which is defined by an angle epsilon as well as a rotation axis. And this is this epsilon normalization that I pulled out here out of the Poisson bracket. We're then going to evolve both the initial state as well as the perturbed state over time, which gives us this deviation delta S. And then we're just going to measure the distance via the decorrelator as a function of time and space. And that is kind of what we're going to plot next. So that kind of has the following form. So this is kind of a plot of a 200 times 200 times 3 spin system. So initially, perturbation was at the very center of this propagating wavefront. So this is already at a finite time value where they've propagated a little bit. You can kind of then go on at later times. It will propagate further until it finally reaches the edges of the system and kind of, because of periodic boundary conditions, then kind of comes back. So there's a few things to note in this plot. The first thing is that you kind of have to believe me, this wavefront actually propagates ballistically outwards. And the exciting or interesting thing is that we observe ballistic propagation, even though I just told you all the thermodynamic properties are fully diffusive. So there's the diffusive structure factor, there's no ballistically propagating spin wave, but we still observe ballistic propagation in this decorrelator. Secondly, this wavefront actually stays isotropic. There actually isn't a symmetry that protects that. So we don't quite understand why that actually happens in practice. And finally, another thing I'm going to discuss next is that this growth kind of at the very front of the wavefront actually is exponential. And actually it moves ballistically throughout the system as kind of a solitonic-like wavefront, which we're going to discuss in the next few slides. So the first thing that I promised you was the exponential growth. The easiest way to extract that is to look at this decorrelator at the side of the initial perturbation versus time and just do an exponential fit to that, which gives me one way to get a Lyapunov exponent out. And you can do that. So this is a plot of the decorrelator at the initial time on a log linear plot at essentially infinite temperature. And what I'm showing you here are two different simulations. One is the full dynamics with a 10 to minus 4 perturbation. And the second one is the linearized equation of motion in black, which also allows you to kind of get this Lyapunov exponent. And what we do see is in the fully nonlinear equations of motion, it kind of starts at the value of the initial perturbation, then grows and saturates essentially at the spin length. But it grows exponentially kind of for this intermediate regime over, 8 orders of magnitude. In contrast, the linearized equations of motion, of course, grow exponentially forever. And that gives you another way to get a Lyapunov, and they're essentially consistent with the fitting errors we have here. So this is at infinite temperature. You can repeat this at any temperature we like and extract the Lyapunov exponent as a function of temperature that way. So this gives us the temporal growth. The second aspect is the butterfly speed. And one kind of practical way to define that is to ask, when does the perturbation at a given lattice side exceed a threshold value d0? And then just performing a linear fit to these arrival times also allows you to define a Lyapunov's butterfly speed. And again, I kind of show you results for that at infinite temperature. But you might be asking, I introduced this threshold value. Does it actually matter what I choose here? And that's kind of what I show here. If you choose this threshold value within a reasonable regime, so it should be larger than the initial perturbation and kind of small compared to the spin length itself, then you see all these arrival times are parallel lines, which means this VB actually doesn't depend on the threshold at all. So this is a well-defined way to define a butterfly speed of propagation of the wave front. We again can repeat this game at many different temperatures and extract the butterfly speed versus temperature. So this now defines both the spatial spread and the exponential growth in our systems. You can also do it in a slightly different way, which is this notion of a velocity-dependent Lyapunov exponent. So you could ask, how does the OTOC or decorrelator depend along rays of constant velocity? And the prediction would be that this always grows exponentially with a velocity-dependent Lyapunov exponent. And there are predictions from Adam, Nahum on what that should look like in different systems generically. And we are kind of in this upper left plot, we kind of have a classical or semi-classical system where this velocity-dependent Lyapunov exponent should essentially behave quadratically, and it should have a zero crossing exactly at the butterfly speed, meaning that within the light cone, you get exponential growth. Outside the light cone, you get exponential decay of the OTOC. So we also tried kind of this way of getting the butterfly speed and Lyapunov exponent from our data. So what I'm plotting here is the kind of scaling collapse. So if you believe the decorrelator has this form, it's an exponential with a prefactor and a quadratic dependence on the velocity with a zero exactly at VB. What you can do is you can take the log of the decorrelator, divide that by t and by the initial perturbation. And what you get is essentially the argument of the exponential. So you directly plot the velocity-dependent Lyapunov exponent by plotting the log of the decorrelator divided by 2t in our conventions. And this is kind of data, whereas the black curve is the fitted velocity-dependent Lyapunov exponent. And you kind of see that the data actually converges onto this scaling form, which then gives us a second way to define both a butterfly speed as well as Lyapunov exponent, in the sense that the velocity-dependent Lyapunov at the zero velocity gives me a mu, which is the Lyapunov exponent, and the zero crossing of this formula gives me a butterfly speed. And we can again repeat this game for many different temperatures to get a different way to get both of those quantities out. The second thing I want to point out is these are the inset as the nonlinear simulations, and there you actually see a build of a wavefront and then perfect ballistic propagation of this wavefront without changing shape. And this is the solitonic ballistic spread that I promised you when I first showed you the decorrelator versus time.
So it looks like there are two different expressions for the Lyapunov exponent on this slide.
Which two different expressions? So there's
so this has like v minus vb all raised to nu, and then the lower bit has 1 minus that all raised to nu.
Oh, sorry, that might be a typo. So the correct one is this one, the one that I have in the fit.
Okay, cool.
Sorry, yeah, that is a typo. Yeah, so it should be the one where the v divided by vb is raised to the power rather than the full expression. So it should be just a quadratic formula like this. Sorry about that. Right.
Sorry, is this now, sorry, is this temperature, what is the temperature here? Is it infinite temperature or?
At this point, it's all, everything I've shown you so far was at infinite temperature. So it's 100 J, which is essentially infinite. We then repeat all of those things at many different temperatures. And you kind of have to believe me that it all works the same way. So I'm going to show temperature dependent quantities next. So far, everything was shown at a single temperature to make it easy, but it works at all temperatures for this chaotic spin liquid.
So does the Lyapunov exponent also depends on the temperature, or it's only just okay?
Everything
so velocity, temperature dependent Lyapunov exponent.
Yeah, that's kind of next thing. So I've now shown you how to define the butterfly speed and the Lyapunov exponent, which are my microscopic chaos notions. There's also macroscopic notion, which was the spin relaxation rate that I defined at the very beginning, as well as the spin diffusion constant. And all of those quantities now will depend on temperature. So what I've shown you was kind of here at 100 J. So I've shown you data points for these 2 points, but we do all of that as a function of temperature. So what this is showing you is the low temperature scaling, and what you actually find is power laws. So if you kind of go below the exchange rate, so J is 1 here, so T1 would be the point where you imagine correlations start to matter. And then below this regime, we actually observe a change from essentially constant behavior to a low temperature power law behavior. The filled symbols are this scaling collapse. The open symbols is this independent way of determining the Lyapunov exponent butterfly speed, and they are fully consistent for all these temperature ranges and simulations. And what we do observe is kind of power law scaling of the butterfly velocity at T2 T2 half for the Lyapunov exponent, and the spin relaxation rate is actually linear in temperature, whereas the diffusion constant is actually constant at low temperature. So these are kind of the temperature dependent findings. There's some things to note here. First of all, the Lyapunov exponent is squarity, which actually would violate the quantum bound. However, this is a fully classical system, so that isn't really a problem. The second interesting thing is that this actually does obey a relation that comes from holographics, where d should be the square of the butterfly speed divided by the Lyapunov exponent, which is what I kind of alluded to. In some sense, there is a connection between macroscopic spin transport and these microscopic chaos notions in this system. And this kind of summarizes what we found in a chaotic spin liquid. So the phenomenology is at infinite temperature, I just have essentially constant behavior. At low temperature, I get power laws for all quantities of chaos, as well as for the macroscopic spin transport quantities. And that kind of concludes this first part where I talked about it, the classical spin liquid. So what I've kind of hopefully demonstrated is that the spin liquid really allows you to study chaos from 0 up to infinite temperature. And we saw power law scaling of the Lyapunov exponent, of the butterfly speed, and of the autocorrelation time. And we found these intriguing connections between macroscopic transport and microscopic chaos quantities, as well as this small remark that actually a classical system can have a Lyapunov exponent that ventures slower than the quantum bound, which again is perfectly fine given that this is a classical system. So it doesn't violate anything in a deep sense. With that, I kind of want to go to the second part where I talk about
Can I ask a question before you move on?
Of course.
So what you presented, I guess, is in a two-dimensional spin liquid system. Mm-hmm. So do you know how this would change if I had for example, a different dimension? I mean, one-dimensional where there is no ordering anyway, or some kind of higher dimensional. So how specific? I mean, rather, how important is the dimensionality, if at all?
Right. So actually, this question will be answered in the next part, where we'll look at it in the ferromagnet in 1D, 2D, and 3D. So that will answer part of the question. If you ask what would happen, say, in pyrochlore, where you have a 3D spin liquid, I would say in principle, it would be the same behavior. I can't know if the power law exponents will be the very same, but as long as you don't order, I assume it will be the same in any system that stays paramagnetic. Of course, as soon as you either do order by disorder, or there's some perturbation that actually establishes order, things will change. So I would say this is generic for any paramagnetic regime in any system.
So if I rephrase what you said to actually, as long as it's paramagnetic and there is no order, they should apply it independent of the rest. Is this correct?
Yeah.
Okay. Possibly with the power laws being different. Okay.
Yeah, potentially.
Possibly, yes. Okay, thank you.
Yeah. So this is kind of the second part. That's exactly what we are asking now, right? So we used the spin liquid because it made our lives easy, because it did disallow phase transitions. But of course, any actual system will have a phase transition eventually, either due to small perturbations or because it is just a system that orders naturally. And then, of course, the big question is, does it matter that I break a symmetry? Because for a classical system, if you break a symmetry, you also have quasi-particles or spin waves. And then you actually have ballistically propagating things in your system immediately, rather than having to rely on chaos to give you a ballistic speed. So you could imagine there could actually something could happen when you order. And then specifically, you could also ask, how does the low temperature ordered state cross over into the chaotic paramagnet, which presumably should be the same as the spin wave I just discussed. Because once I'm paramagnetic, you don't know that you are not a spin liquid, essentially. And these are now the systems exactly I'm going to discuss. So it's again a Heisenberg O3 spins on lattice sides, and we're going to do it in 1D, 2D, and 3D, again, both for ferromagnets and for antiferromagnets. which essentially exactly answered this question. One comment, of course, is that at 0 temperature, all of these states have a fully ordered ground state because they are bipartite. So both the Néel state for the antiferromagnet and the fully polarized ferromagnetic states are perfectly good ground states. Only the three-dimensional system, of course, has a finite temperature phase transition. The systems in 1D and 2D don't order in the thermodynamic limit. They do, of course, order on finite systems. So essentially, if the system is small enough such that all spin waves are gapped out, you also get order again, which goes back to my very first comment where I talked about these different ensembles. In principle, what we are asking here is, what does an ordered state do differently than a paramagnetic state? So in some sense, I don't care if it's a thermal phase transition, as long as I can define an ensemble that gives me a finite magnetization and the ordered state has spin waves, that is good enough for me. So even though my results in 1D and 2D are not in the thermodynamic limit, they're perfectly well defined for asking a question, what does a state with a finite magnetization do compared to a state that doesn't have a finite magnetization? And again, we kind of use semi-classical dynamics. It's the same story as in the spin liquid. So let me start with the thermodynamics again. For the antiferromagnet, the order parameter is the staggered moment. For the ferromagnet, there wouldn't be a sign. And as I said, actually, in finite systems, all of this order. So the three-dimensional system, which are the squares, has a perfectly well-defined transition, both for the ferromagnet and antiferromagnet. On a finite system, also the 2D system shows a very clear phase transition, which is a finite size transition here. The 1D system actually only shows a very slow kind of crossover where the magnetization kind of increases as a power law as I go lower in temperature. So this is the order parameter. You could also ask the question, what do the correlations do? So in the paramagnetic regime, they are exponentially decaying. And if you extract the correlation length as a function of temperature, that will also show a phase transition, where it essentially is on the order of a lattice side. And then in the ordered regime, it jumps to the order of the system size. And that's what I'm showing here. So these are systems of about 100 to 1,000 spins. And again, at the transition, the correlation length jumps from one lattice side to essentially system size. So both the 3D and 2D system on a finite size system show perfect long-range order, essentially. The 1D system, again, crosses over a bit. So this one is slightly different than 2D and 3D in practice. So that is why also the 1D system will show slightly different behavior in what I'm going to show next. And then what you actually find is there's 3 different regimes of this decorrelator. So there's an initial regime to the very left. So this is kind of a busy plot. Let me start at the first column. So this is short time scales and short length scales. And I'm comparing the full numerical simulations to linear spin wave theory here. You kind of see that at short times, linear spin wave perfectly describes the full dynamics of the decorrelator, also quantitatively. Then if you go to intermediate times in the middle column, intermediate times and scales, you kind of see what we kind of call a scar-like regime, where you seem to observe kind of particles that scatter off each other, that kind of get reflected or pass through each other, as well as growth of the decorrelator in terms of magnitude. And finally, there's a very long time and long length scales regime where the decorrelator becomes chaotic with kind of a linear light cone and a diffusive core and exponential growth in that regime. So this is kind of the phenomena we find in a system that orders and across different time and length scales. And I'm going to go through each of these 3 regimes kind of in more detail next. So there's what we kind of call a short-time integrable regime. Left is ferromagnet, right is antiferromagnet. Upper row is 1D, 2D, 3D. Left row columns in each are linear spin wave, right are the full nonlinear simulations. And all I'm gonna want you to see here is that essentially at short length and time scales, the linear spin wave theory qualitatively and quantitatively describes the system dynamics for all of these cases. And what do I actually mean by linear spin wave theory? So the basic idea is at low temperature, we know that I have an ordered state, and then I can expand my spins as an ordered moment and some spin wave amplitude, and just expand my equations of motion in the spin wave amplitude. And if you do that, you get equations of motion for the linearized decorrelator that has terms where the magnetic moment interacts with the perturbation, as well as the spin wave amplitude scattering off the perturbation, which is the second and third line. And then finally, there's nonlinear terms where the perturbation interacts kind of with itself. And this in principle defines a perturbative diagrammatic series for what the decorrelator does, which you can in some regime solve. And that's what we did do. So the very first thing you can do is you can kind of neglect all interactions. So you just take the zero order solution. And that is what essentially defines the linear spin wave theory. And if you do that, you get a prediction of what the decorrelator should do, in this case for the ferromagnet, because it's slightly easier to write down. The important thing to note is that it fully separates over dimensions, and it kind of has a Bessel function as well as a time argument, which allows you to define butterfly velocity based on linear spin wave theory, as well as observing that this predicts power law decay T2 minus D in D dimensions within the light cone. And most importantly, it tells you that the sum decorrelator in the linear spin wave theory should be constant. So the basic picture that is true in linear spin wave theory is I put in a perturbation and that just ballistically expands. So that's why the amplitude must decay as T2 minus D, because I escape into a volume of size T2D ballistically. And in addition, of course, the total amplitude that has spread out must be conserved, which is the sum rule. So you can now actually sharply define when am I in the short time integrable regime and when do I see chaos, by asking when does this sum decorrelator deviate from the initial value, which was 1. Just to show you, this is actually the full comparison of these simulations at different lattice sites versus time between the full theory, which is the full curves, and the numerical simulation, which are the dots. And they actually fall perfectly on top of the simulation at the initial times. So there's very good quantitative agreement as well with this linear spin wave theory initially.
Sorry, Thomas, can you show the previous?
Yeah.
So what is, so the dotted line is the full calculation?
So the orange curve is this formula.
Yep.
And the points are simulations at a specific sampling time. So the simulations only sample at certain times, and that's why there are these dots. And they essentially, they would be fully on top of the curve if I had sampled more finely, but this is the time step where I just saved the spin dynamics.
Okay, so sorry, I'm probably sort of way behind you, but so you really are plotting the decorrelator here.
Yeah, this is the decorrelator
at a given point versus time.
Yeah.
So why does it decrease?
Well, it spreads out. Initially, it's a ballistic spin wave. So it expands into a volume ballistically, which has volume T2D, which means the amplitude must decay as T2 minus D.
But it's not conserved, right?
It is in spin wave. It initially, before you get chaos, it is just a ballistically spreading blob.
I see. Okay.
That's exactly what we observe here. That's why we call it integrable.
Okay, thanks.
Right, and that's now the next question is of course not conserved. You're perfectly right. So initially, this sum decorrelator weakly increases for times that are small compared to the Lyapunov time. So if you look at this inset, it starts at 1 and it only increases very slowly initially. In contrast, if you wait for a long time, you actually see on this log plot perfect exponential increase of the decorrelator. So there's a somewhat a crossover where before the Lyapunov time, I get power law decay. After the Lyapunov time, I get exponential growth. And this now goes into the onset of chaos. Initially, I'm spreading spin waves. These spin waves start to scatter and they start to grow exponentially, which then gives me this scarred regime. We also did some more theory where we can actually connect the spin wave lifetime to the Lyapunov exponent exactly by its argument. So the idea is spin waves spread initially ballistically. Once they start interacting, they can decay. And it is this spin wave scattering that gives you a finite Lyapunov exponent in the ordered regime. And that then gives me the scarred regime. So again, this plot, you have initially ballistically propagating spin waves that just spread out. They start scattering, getting reflected, and then start growing exponentially in this light cone as well. And you can kind of look at this very evocative plot and ask, are there other ways to define this collisions, and there is a way you can ask, what is the position of the maximum of the decorrelator at a given time slice? And you kind of do see that this actually observes very clearly defined ballistic collisions where it just reverses the direction. So what we are really seeing is in the low temperature regime, there are ballistically propagating excitations that in addition grow exponentially in time. And the propagation of these scattering events then leads to chaos and exponential growth. So this is kind of the phenomenology you just see in the simulations very clearly when you look at the decorrelator. And then finally, if you get lots of these scattering events, the background gets perfectly smooth because many of these light cones and scattering events overlap, and you get this exponential behavior and a diffusively defined core of the decorrelator. And that kind of defines what we saw in a kind of classically ordering system. Another cute thing is that the ferromagnet and antiferromagnet actually show different dynamics, which makes perfect sense. So I told you that, of course, the thermodynamics must be identical. The dynamics don't have to be identical because spin waves have different spectra for ferromagnets and antiferromagnets. So specifically for the ferromagnet, you get this factorization over dimensions. So you get kind of square-like wavefronts. The antiferromagnet actually has circular wavefronts. Again, spin wave theory matches very well quantitatively with the full simulations, also in 2D. And then finally, does all of this matter for the chaos quantities? So again, we now look at the Lyapunov exponent as a function of temperature. And what I'm showing here is at the point, this is a 3D system, so the magnetization actually goes through a phase transition and it grows to a finite value. And at the same point where that happens, you see that the Lyapunov exponent changes from essentially constant to low temperature power law scaling. So again, it's power laws, and the power law changes exactly at the phase transition. The same thing is true for the butterfly velocity. Again, at the point where the magnetization goes through the phase transition, goes up, the butterfly velocity also changes. So what we are seeing is that the phase transition actually significantly changes the chaos properties exactly at the transition point. So this was in 3D for the ferromagnet. You can again ask this question for ferromagnets and antiferromagnets and the butterfly velocity and the Lyapunov exponent in all dimensions. And as I kind of told you, the 1D system is slightly different usually. The 2D systems and 3D systems are consistent with just having a proper thermodynamic phase transition. So again, all dimensionalities change from constant to power law decay across the phase transition with slightly different exponents. So these actually are now factor of 2 if you have a proper phase transition rather than what we found in the spin liquid. So it's a different exponent for all of those. In contrast, the butterfly velocity actually goes up below the transition. And if you ask what is the prediction of linear spin wave theory, which are these black dots, they actually very well match the numerical simulations as well. So what we are seeing is that the chaotic speed that is defined at high temperature actually gets replaced by the spin wave speed at low temperature. So this butterfly velocity has a minimum as transition and then grows as the ordered moment and the spin wave speed increases in the ordered regime. And that kind of summarizes what we kind of found in the thermal phase transitions. This phase transition changes characteristically what the Lyapunov exponent and butterfly speed do. And the magnons essentially replace the chaotic butterfly speed once ballistically propagating particles are present in the system that can just ballistically spread out in initial perturbation. And I showed you how this scattering of magnons, at least intuitively, then leads to the emergence of chaos, both in terms of these particles that reflect each other. And we had these scarred regime where along these trajectories I actually saw exponential growth of the Lyapunov exponent along rays that did propagate with the spin wave velocity. And I showed you some argument how in perturbation theory, this magnon lifetime can actually be related to the Lyapunov exponent in the sense that it is actually scattering that leads to exponential growth eventually. And that kind of concludes the second part about phase transitions. I have a short section about the anomalous dynamics if you have time. But depending on what people feel, we can either go to questions or I can do the last part as well.
How long will it take?
It's like relatively short, so I could do it in...
It's okay,
yeah. Right. So this was the very last part, which was kind of asking, okay, I showed you these kind of emergent spin waves in the 1D Heisenberg chain. And you could now ask, okay, does this actually change the long time equilibration, thermalization, and hydrodynamics of this system? So can we expect departures from, say, diffusion because of the kind of emergent integrability I kind of just discussed? And the reason why this is interesting is we just look at a 1D classical Heisenberg chain here, ferromagnet, antiferromagnet, is that to our surprise, actually nobody knows what the hydrodynamics should be. So there are papers that argue that it should be fully diffusive at infinite and at finite temperature. There are some works that claim it should be non-diffusive even at infinite temperature. There's works that argue the diffusion constant should be log enhanced. And there are some works based on non-abelian hydrodynamics that there should be squarity corrections to the diffusion constant. So surprisingly, this most simple 1D system, a classical Heisenberg chain, people don't actually know what the hydrodynamics is. And just to give basic introduction, what do you normally expect? If you have any conserved charge, you can define a transport equation of this form. And then if you just do gradient expansion for currents, you always expect diffusion. So typically, if you don't have something else, a system classically with conserved charges should just show classical diffusion. There are some ways out. You can have integrable models. You can have fracton models, which I think people talked about in the seminar series already. So there are some ways out. But for the classical Heisenberg chain, we don't know that any of these things would apply. So we don't have other conserved quantities. We don't have something that would forbid the first derivative. So the most naive expectation would be it should be diffusive. And that's what we try to check numerically. So we look at the energy correlations as well as the spin-spin correlations, and we try to get hydrodynamic scaling. So usually you would expect a correlation function to behave in this universal form. There should be a T2 minus alpha prefactor, as well as a universal scaling function, which could be a Gaussian if you have diffusion, or it could be, say, a KPZ scaling function, or anything else you want to put in there. And this autocorrelation function then also defines the decay of the autocorrelation function itself, which has the same power alpha. So you can get this alpha directly from the autocorrelation function. And that's what we did. At high temperature, in blue, the ferromagnet and the antiferromagnet is perfectly consistent with diffusion. At low temperature, it is not. So we clearly observed that the ferromagnet shows an exponent that is intriguingly close to 2/3. So this only tells you that it is not just diffusive dynamics over extremely long time. So these simulations go up to 10 to 5, and the ferromagnet doesn't show diffusion in this system at all, up to these very long time scales. Moreover, it is not only that
is there any physical reason to expect that you would get diffusion? I mean, it's a chaotic system, so there's no noise, no Markovian processes, right? So
well, it is a normal thermal state that has just conserved charges, right? You would expect diffusion to apply to that for any classical system if you don't have something else. That would be the standard hydrodynamic expectation at long times.
Okay.
If you just sample thermal states for a classical Heisenberg system that doesn't order, you would just get diffusion for the conserved spin density.
Mm-hmm.
Just because there's a blob that is totally conserved and it will just spread out diffusively if you don't have ballistic propagation in some sense that could carry the charge.
Well, it could be subdiffusive or superdiffusive, right? I mean,
right. Yeah. But generically, if there's not something else, it should typically be diffusive. That would be the standard expectation. And that is also true at infinite temperature. So yeah, there you kind of get what you expect.
Yeah. Okay.
So not only is this exponent not diffusive at low temperature, even more so, the full scaling function is actually KPZ. So what I'm comparing here is using the exponent we get at low temperature. And in this collapse plot, the dotted line is a Gaussian scaling function. The dashed line is a KPZ scaling function. And this is, I would say, very convincing data that shows, at least for finite times, the 1D Heisenberg chain actually shows KPZ hydrodynamics, which to us was very surprising. And that's kind of all I wanted to say. It's kind of cute that in the most simple model of a spin system, we actually find KPZ scaling. And importantly, we don't find any evidence for log corrections. We don't find these T corrections. Actually, we do find finite time KPZ instead. Yet with that, I want to thank you for your attention, and I'm happy to answer any questions or discuss further.
Right. Thank you very much for this great talk. So we can stop the recording now, and we can start the discussion.